the design of the ice maker in your domestic refrigerator. Ice making. Well, the heart of it is a refrigerated surface. It's called evaporator in the fridge, which is at a temperature T wall. This is a wall. Refrigerated means that it's being cooled. A temperature that's lower than the freezing temperature of water. So here is water ready to freeze, meaning at the freezing point. And on the cold surface accumulates a layer of ice. A layer of ice of thickness delta. A thickness that increases in time as square root of alpha t. By the way, that was the mistake on the blackboard. I just figured out that this delta is square root of dt, not d square root of t. That was why d persists in the analysis. I just remembered. Anyway, delta increases as square root of alpha t. Okay? In other words, you create ice on a refrigerated surface. However, in time, the process runs out of zip, meaning that layer doesn't grow fast anymore. So you have to get rid of it. That's why I drew the layer vertically, so that you can imagine the gravity pulling it, and you hear the clunk in the bin of the freezer. Everything is familiar. So that the second time interval, if the first one is T1, is the time interval during which the manufactured ice is removed. So ice removal means cleaning the surface. Here you see how the ice maker is coughing all the time. These people, by the way, who designed another thing, you've seen these trays, ice trays, they have little cubical alveoli, and that's a design for removing a whole bunch of these all at once after you pull the tray out yourself, okay? All right, so there are two time scales. This is freezing time, and this is the time of surface renewal. The mechanical time T2 requires a design of its own, meaning not the object of my lecture. So I will assume that this T2 is the baby of that other design that I will not talk about, meaning that T2 is a constant given to me by engineers from the cubicle next door. So this is assumed known. So then what is the object of the game? The object of the game is to figure out T1. This is the degree of freedom. Degree of freedom. And this is selected rationally with objective or purpose. And the purpose is to maximize the time averaged rate of production of ice. What is that? It is the thickness of the layer called D1, delta 1 at time T1 divided by the duration of the cycle, which is T1 plus T2, also known as In the book, I did not write this. I wrote that delta from measurements actually is some constant b, and then square root of t. In other words, it's b and then square root of t1 over t1 plus t2. It is a wonderful opportunity to review the trade-off between Roman 1 and Roman 2, meaning the degree of freedom is T1, and there are two extremes. I define this degree of freedom in dimensionless terms as T1 over T2 because T2 is known, and I call it tau. So the so-called object of the game varies as square root of tau divided by tau plus 1. The so-called average rate of ice production varies as tau to power 1/2 over tau plus 1. This has two kinds of behavior. In the first one I wrote is if tau is a lot less than 1, that means short freezing time T1, then this thing varies as tau to 1/2 because tau is less than 1. And the other extreme, tau much greater than 1, it varies as tau to minus 1/2. And the intersection of the, you can make this graph, it's easy to make. Should I? Delta average versus tau, 0, 0. This is Roman 1. This is Roman 2. And Roman 1 goes as this. Roman 2 goes as this. And then the intersection of the two obviously happens here, but it does signify the location of high values of delta. And they happen at tau over 1, which means a freezing time T1 dictated by the time of removing or cleaning the surface. And this is, of course, very good news for those colleagues next door who design mechanical ways of scraping the ice off. Beyond this example, your mind should run wild to see equivalents from your domestic life all the way to back to animal design. Domestic life, the windshield wiper in the car is the same idea. It is actually a very famous story, this windshield wiper. In the 70s, early 70s, there was a nobody, a very modest, I don't know what he was doing, maybe working in a car repair shop, who invented the rhythmic windshield wiper. And luckily, he patented the invention. And then a few years later, Volkswagen vehicles appeared with this timed thing of cleaning the window. And famously, Volkswagen got sued and had to pay this simple man millions. This is in the early 70s. Meaning, to all of you, if you have an idea, make sure you document it or talk to a lawyer. That's number one. So windshield wiper. The equivalent in animal design is the movement that inspired that inventor, which is the movement of the eyelids. The eyelids are going rhythmically. You are not aware of it. The eyelids are doing that to the eyeball. They lubricate it, they clean it, they again, read the love stories. It's all about better life, and 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 there are other even more useful counterparts to this part of the lecture, which of course I will tackle next time. Heat exchangers. This is all over industries globally. They they're full of fluids flowing through ducts. The ducts are either heated or cooled, but the heated ones end up being clogged by debris or gunk. Gunk on the inside surface is called scale. Scale is a deposit that's very similar to the plaque on the teeth, and the heat exchanger, meaning the power plant, has to be shut down so that its tubes are scraped clean internally. See that? And when you shut down the power plant, you register a cost of not the producing power, which of course you could sell. So that's one topic that will entertain us when we reconvene on Wednesday.